Awesome. Well, let me share with you a topic that is of a special relevance to me, that is the weld pool. I did my PhD on this. I read much, I did quite a few experiments, and some of my PhD students have also worked on this. And what I'm going to show you is something that all things you get to see, right? And some things that not people often have not put together. So let's go with, where's, I lost my pointer. Oops. Okay. No. All right. All right, I think there was a little bit of a comedic interruption. Somehow I had lost my pointer and my computer froze. So the weld pool, things we get to see. That's where the molten metal is. So in our previous block of slides, when we discussed the isotherms, right? The melting isotherm is the edge of the weld pool. Whether we heat fast or we heat slow, or whether we cool fast or slow, the edge of the weld pool is pretty much the melting temperature. Other temperatures, for example, transformations in the solid state transformations, are quite affected by heating and cooling rates. But melting has relatively little effect for the typical velocities present in welding. For some cases of additive manufacturing, this might not be the case. For example, additive manufacturing in powder beds, in which the laser causes very small local melting and the cooling rates are enormous, there might be some deviations from melting temperature, for which there are formulas and for which our predictions of heating and cooling rate are still very good. These formulas you have, we have tested them. They are amazing, actually. So, but overall, we say melting temperature, and that defines the weld pool. The size and the shape of the weld pool depends on the process parameters, depends on what process you're using. And you have many physical phenomena present in the weld pool. And this is what makes welding so difficult. Let me tell you, a welder grabs a torch and welds. Regardless how many PhDs the welder has, or no PhDs, or reading and writing, you can still weld. You design a rocket, you imagine von Braun and many smart people that for sure have lots of studies. But let me tell you something, understanding welding is way more difficult than rocket science, because we have solidification, but rocket science doesn't. We have plasmas, which they seldom have, maybe in re-entry. We have phase changes, which they're not meant to have, right? We have electromagnetics, not really. You don't weld without all those things playing for you. If all those things don't work for you, you don't weld, whether you know it or not. And in this class, and in the research we do in the lab, we're trying to understand that way beyond the simplicity of like aerodynamics and associated things. So what we see in the weld pool, we see heat transfer, we see fluid flow, we see capillarity, right? The effect of surface tensions. We see electromagnetic effects, and we have already talked plenty about like the jet in the plasma or the pinch force in droplet detachment. We have surface interactions like gas shear and gas pressure. We have evaporation, right? Fumes come from molten metal that is evaporating. We have chemical reactions, and those are infinite, right? Like fluxes. How do the fluxes suck up oxygen, right? All chemical reactions. So all that is happening in the weld pool. You see just a little bit of molten metal. Well, it's a whole lot more than that. Let's start with something that is pretty cool. This is like when I said welding in steels work for a miracle of God. There are a number of reasons they work, but haven't you ever wondered why a weld has the size it has? For example, you don't see welds that are 1 micron in size. And you don't see welds that are 1 meter in size. A weld bead is not 1 meter. And you might say, of course not. Yeah, why? Because many other things are. Milling machines can be enormous or can be very small, but welds don't. And here's an interesting thing about welding. In welding, the size of one bead is given by the laws of nature, and nothing we can do about it. And the forces at play are the surface tension. So the droplet has its weight, the molten metal has its weight, but it's kept in place by the surface tension. And there is a dimensionless number that compares the weight of the droplet and the surface tension keeping it in place. And that is called the bond number. So, and more or less, when bond is bigger than 1, means the droplet will flow like a splatter all over the place. When bond is less than 1, it's going to turn into a ball, right? And keep in place. So welding in general seldom exceeds a bond of 1, because if it exceeds a bond of 1, means we have such a large weld bead that it's going to be running down the groove. Typically, that's not what you want. So let's use this bond number that comes from fluid mechanics. And if I say, okay, let's say that welding is limited at the bond number of 1, this is very rough, right? I would predict that the biggest size of my weld, right? Here we have, I didn't say in these symbols, this is density. Rho is the density of molten metal. G is gravity. L is one characteristic size of the bead. Let's say is the height of the weld bead. And gamma is a surface tension. So I can solve for the size of the bead, and it's going to be solving this equation on top, square root of surface tension divided density and gravity. If I put in numbers for steel, I get a weld bead of more or less 4.7 millimeters. Right? This is not an exact number, but this is the number of a weld bead. You don't make, so this would be short of a quarter inch. You don't make weld beads a whole lot bigger than this. And if you wanted, you know what you do? For example, you use flux core electrodes in which the flux helps keep the weld in place, the molten metal in place. This is the main reason why we would use gas shielded flux core electrodes. So we already discussed this. Why would I use a flux core electrode if I'm using a gas anyway? Right? But flux core electrodes give us a quality somewhat similar to MIG, but in addition, they give us a way of cupping the bead so it's not going to run crazy and we can make bigger beads. This is important too, for example, in the case of vertical welding, out of position welding, right? Pretty cool. If we do the same calculation for aluminum, we get 5.8 millimeters. Of course, aluminum has more or less the same surface tension, but it's a lighter metal, right? And so what we see, whether it's steel or aluminum, or you can do this with titanium, but you're gonna see that a weld bead is always give or take 5 millimeters, right? Give or take, this is not an exact number, but for sure it's not 5 centimeters, And it can be smaller, although it comes with a challenge. Typically, too small beads, capillarity is too strong, and also cooling rates are too high. How interesting. Question to you. If I start welding on the moon, can I make bigger welds? Would I be more productive? Thoughts? Yeah, we have less gravity. We could make bigger welds. Yeah. Now let's say we make bigger welds, right? And we're happy and we're making welds that are massive. Anybody can think of a way why I wouldn't want to make such a huge weld? Okay, interesting. So if I were to have such a huge weld, that means it would take very long to cool down. Regardless gravity, the heat transfer doesn't care about gravity. So we might end up with a problem of coarsening. For example, we have huge welds when we do electroslag, right? Or electrogas welding. And the problem with those are huge and they are very productive. But we have an enormous coarsening in the heat affected zone. So I want to go over some of the questions. I have a suggestion that reduced gravity would cause reduced penetration. And it is, penetration has quite little to do with gravity. I'm gonna discuss this in the next slides, although I acknowledge that if you flip the weld and you're doing overhead, you tend to have less penetration, but that's typically because the weld bead is smaller, because you don't want it to fall on you. I have a comment about larger heat affected zone. Of course, it would be a huge heat affected zone and we can predict it. But with the formulas you guys have, you can predict if you weld on the moon, how big your weld can be, how fast or slow is going to be, the cooling, and the hardness is going to have. You're super powerful. You're very different than most other people who learn welding from a catalog. You don't need to come to engineering school to read a catalog. But with these things, if I ask you, okay, we're going to the moon, design me a welding machine, you say right on, and that's cool. Okay, another one. Yes, a huge weld would have issues with shielding gas too. Big welds, and it's the case of subarc welding, the tail starts to become very long, right? Although, yeah, depending how we do it in the moon, we might not need a whole lot of shielding, right? Right, if we would need shielding gas in the vacuum of space. Depends, but I show you a photo of electron beam welding in space, in which it was done with no shielding gas, right? So interesting, right? And if you're in outer space, in theory, you can make a weld be big as a soccer ball. I'm not too sure we want to do that now, but we can think all these things now. We're at so much higher level now, as we discussed, way beyond what is in a catalog. All right, here, let me tell you something else. There's something interesting, and I'm showing you this very complex graph here. I don't want to get into the details right now, but this graph says what the surface tension is for steels versus temperature. And each of the lines corresponds to steel with a little bit of sulfur. So this big line here says no sulfur. This one says a little bit of sulfur and more sulfur. But the bottom line here is, if I have a steel with very little sulfur to none, I would have a surface tension of the order of 1.9 Newton meters. And if I have a significant amount of, sorry, I said sulfur. Sorry, I said it wrong. Everything I said would be the same, but this graph is about oxygen. So sorry, this is oxygen. If you have no oxygen, you have a high surface tension. And if you add more and more oxygen, the surface tension is lower. essentially because the oxygen is satisfying some of the unsatisfied bonds on the surface that are the source of surface tension. So essentially the oxygen is relaxing it a little bit. And what this says is that depending on whether you have low oxygen or high oxygen, you're going to have a different maximum size of the bead. Now let me tell you a super cool story. I don't know this from firsthand because I'm not a good enough welder, but I have good enough welder friends. And let me tell you one story I was told. If you're doing vertical up fillet welding, you're at the very edge of what how much capillarity can hold your droplet. At the very, very edge, it's a little bit bigger than you need to do, and the molten metal is going to run down. So this friend is welding vertical up, having a happy life, and all of a sudden finds a rust spot. It's a spot, a rusted spot in the plate. He keeps welding. And you know what happened? The bead came down rolling on him. Why? Is the oxide having the effect of Teflon on the weld? Right? Isn't this amazing? What happened is that when he started to weld over the rusty spot, all of a sudden, the surface tension, instead of being this surface tension that can hold up the droplet barely but hold it, the weld pool, it became too weak to hold the bead. And the bead came down rolling on him. This is awesome. So you get to see how we're talking about like some kind of sciencey things, but we can explain what happens and people are like dumbfounded. So morphology of the weld pool, right? What we talked about this Ricalin number that is some sort of a measure of fast versus slow. And when we're fast, the weld is elongated. And for reasons I don't fully understand myself yet, the elongation is not like a perfect ellipse, but actually gets quite straight edge here. I think because the kinetics of solidification get affected. And in this case, what we see is that the dendrites, right, the solidification structure grows pretty much like perpendicular to the axis of the weld. In some cases, as it grows perpendicular, we have a problem because if you remember your phase transformations class, in which as you solidify things, you segregate the impurities to the front, right? As the two sides of the weld, the top side and the bottom side, they start to solidify and both sides keep pushing and rejecting the impurities such as sulfur or phosphorus to the center. The center then might end up full of contamination, and that can cause hot cracking, can cause problems later down the road. If we have a slow speed, we see something interesting. That is, we see that these dendrites start to grow always perpendicular to the edge of the weld pool. And we see then how they started to grow perpendicular to the travel direction, and then they start to bend, right? This one is on the left, bottom left is the best. The dendrites start to grow and they bend around. And we would see then in the solidification structure, we can tell whether we were welding fast or welding slow by seeing the structure of the columnar grains from solidification. This is pretty cool. The people who get deep into the issues of metallurgy, they need to know this fast versus slow business because of this segregation that causes impurities. This is powerful. And all this traces back to, if you ever want to do things quantitative, we're not doing it here. But for solidification, there are lots of formulas that tell you dendrite arm spacing, that tell you growth velocity, many things. And all those require parameters such as cooling rate. Typically, people who do solidification, they don't know all the heat transfer, but you know all the heat transfer now. I want to discuss, in the time we have, the mechanisms of penetration in welding. This is seldom discussed specifically, but there are 3 different mechanisms of penetration that are so different one from the other that you cannot extrapolate what you learn in one to the other. 2 of those we have already discussed. One is this, what they call conduction mode. I don't like it because actually it's convection. So I call it recirculating flow, right? And I'm gonna show you in the next slides what I mean by recirculating flow. But this is characteristic of low welds that have low currents, or power beams like electron beams or lasers that are relatively low power, right? Or and also typical in slow welds. Now, the other one, I'm jumping here to the bottom, which we had already seen, is the keyhole mode, in which we have high power beams, right, that drill into the plate. There is something we have not discussed in, I might have not like just mentioned in passing, that is what is called the gouging region mechanism of penetration. This is something that is kind of halfway between the recirculating flows and the keyhole. The keyhole is driven by evaporation. The gouging region is not driven by evaporation. This is what in people welding with 6010, what they call the keyhole, right? Especially if it penetrates through the full thickness. But what is happening here is that the power, the pressure of the arc, that electromagnetic jet we have discussed before, right? It comes here and pushes the molten metal back. So this is characteristic of high current welds. So the one on top is characteristic of low current welds or beams, and this has to be an arc weld in which the arc pressure pushes the molten metal back. This, for example, is a typical case of penetration in submerged arc welding because we have high currents. So let's discuss recirculating flows. This is a really cool story, which I got to see from close when I was a professor in Colorado. In the 80s, right, at the height of the Cold War, people were making atomic bombs. And among the places in which we were doing them, it was in Rocky Flats, Colorado, right in the middle of the country where like it's very difficult to invade, right? And let's talk about the hydrogen bomb, in which it's so powerful, but you need to trigger with another bomb, right? It's crazy on top of crazy. But those things, this trigger mechanism has to be a perfectly symmetric sphere that is welded, right? And it has to be perfect because in the nanosecond it takes the detonation to happen. You cannot have one part that starts earlier than the other or that is a little bit farther apart from the other. And so we have these plutonium triggers, and they were welding them using TIG. And they saw this. They saw that the same material with the same gas, with the same welding procedure, with the same torch, sometimes it would give you good penetration, sometimes horrible penetration. Same material, same procedure, same welding current, same everything. Wow. What do we do then? And they start to do all kind of correlations and look at things, and people postulated theories, some of which probably they wished nobody would remember they postulated them. But this is a very real problem, and none of the knowledge up to that time could explain what was happening. And what happened is this thing that I'm going to explain to you here. I'm going to, let's see. Okay, let me tell you a little bit more. They saw that the welds that had bad penetration had a little bit more of aluminum. That's all as far as they could see, a little bit more of aluminum. Eventually, they figured this out. They figured that the welds with higher aluminum were deoxidizing the steel. And the steel without oxygen had one type of surface tension, and the steel that had low aluminum and had more oxygen in solution had the other type of surface tension. And that caused the difference in penetration. So I'm going to tell you a little bit about like how these recirculating flows work before I get into what was happening. Recirculating flows. In the whirlpool, right? Like the travel speed is relatively small compared with the velocity at which the molten metal moves. When you have a hot metal and cold metal, you would have buoyancy forces, and you have natural convection of the type we studied in the heat transfer class. And this is natural convection in an enclosure, and we can make some sort of predictions. But the predictions say that the velocities due to buoyancy would be of 1 millimeter per second. At the same time, because we have an electric current because it's TIG, we have electric currents going through the whirlpool, and those electric currents can cause also an electromagnetic force and have some sort of internal electromagnetic jet inside the whirlpool. And people calculated those. Lots of work, even in the 80s when computers were like small and clunky and way less powerful than your phone, they were calculating those things. And they saw that these electromagnetic forces would be of the order of centimeters per second. Another force that can drive the molten metal is if you have the gas that moves on the surface of a liquid. So because of viscosity, that gas drags the surface, right? This is the way in which the wind causes currents inside the lake, for example. The wind rubs over the surface of the water and starts to drag the water. And in this case, the plasma wind drags the surface of the whirlpool. And typically when we have recirculating flows, the velocity is of the order of 1 centimeter per second. But they were measuring 1 meter per second with high-speed videos. You try tracing impurities. You measure 1 meter per second, 100 times more. And then what they saw is this other mechanism that is called the Marangoni flow type of Marangoni forces type of flow. And the changes in surface tension create fluid flow of the order of 1 meter per second, right? This, when we have recirculating flows, this is the dominant type of the dominant mechanism driving the molten metal flow. And by the way, depending on the direction of that the fluid flow goes, it can help or hinder penetration. So you had already seen this graph, but let's look at it together. And has one very important feature that I didn't discuss before, but I was waiting for this time. This straight line here in the top is when we have steel without oxygen or without sulfur, right? Pure steel. And it says that at low temperatures, we have high surface tension. And as we increase our temperature, surface tension decreases. To some extent, it's more or less like saying that higher temperatures weaken the surface tension. Now, let's say we have some amount of oxygen, and this also applies for sulfur. It says that at high temperatures, it doesn't really matter. It's as if it was pure. But at lower temperatures still in the molten metal range, right? This oxygen reduces the surface tension. And at lower and lower and lower temperatures, the surface tension is more and more reduced. I want to draw your attention that when we are in a pure metal, higher temperatures mean lower surface tension. But when we are in a metal that has these surface active elements such as oxygen or sulfur, the surface tension increases with temperature. How paradoxical. Higher temperatures mean stronger, higher surface tension. So what? All right, this is what happens. Let's see here in the bottom a weld pool. And in this weld pool, we would have this distribution of temperature, right? This distribution of temperature, which comes from the equations we have discussed, the Rosenthal equations. And let's say that we have a metal that is pure, no surface active elements. So with higher temperatures, lower surface tension. And in this case, the axes are flipped because I wanted to put the vertical axis as temperature in both. And here the horizontal axis is surface tension. So high temperatures, low surface tension, and higher surface tension corresponds to lower temperatures. Okay, look at this. In the center of my weld, bead, I have the hottest temperature. That means the lowest surface tension. And at the edge in which I reach melting temperature, have lower temperatures, therefore higher surface tension. Aha, arc blow. That was speculated too, but in this Rocky Flats, the problem was not arc blow. So look at this. Now, because we understand the temperature distribution, and we just discussed the relationship between surface tension and temperature, I combine both, and I would see that here at the center, I have low surface tension. Here at the edge, I have high surface tension. So the net effect is that on the surface, I have a force that pushes the surface of the liquid outwards in this form that is illustrated here. The flow goes out. Now, if the heat comes here on the surface, I want to ask you, do you think this sense of recirculation that is towards the outside would give us higher or lower penetration? What would you expect? That this is the deep weld or the shallow weld? Yeah, low penetration, exactly, that's what happened. And that's why they saw this effect in the welds with higher aluminum, because with higher aluminum, you suck up all the oxygen because aluminum is a very powerful deoxidizer, and they were having essentially a pure metal that didn't have penetration. Let's look the opposite. Same temperature distribution that comes from our equations. But let's say now that we have a metal that has some amount of oxygen or some amount of sulfur. Then we would see that the surface tension, that in this case is in the horizontal axis, the surface tension is decreased, the surface tension increases as I increase the temperature, right? Opposite behavior. Surface tension increases with temperature. And then what would I have? Higher surface tension in the center, a low surface tension in the edge, which means the center is pulling the fluid into the center of the weld. And if I pull it into the center of the weld, then it comes down kind of as a hot jet. This gives us a lot more penetration. Just think how amazing this is, because the heat source is the same. The metal looks the same. They thought, and the funny thing is that these differences in little amounts of aluminum or little amounts of sulfur tend to be within the range acceptable for material specification. So the range, the small variations in oxygen or in sulfur are within the same spec. So when I told you it's the same material, that's what they thought, because it is same 304 stainless steel. But it wasn't exactly the same. There was a difference, of course, but the difference was within the specification. So in this case, we have high penetration. If you don't control in your case, the oxygen through aluminum, or you don't control the amount of sulfur, you can have some days high penetration, sometimes low penetration. Let me tell you more, something very interesting. Modern stainless steels are done with vacuum furnaces, are done with such a high level of purity that have close to no sulfur and close to no oxygen. You know what? Modern stainless steel sometimes have a problem of penetration because these Marangoni flows go out and don't go in, and the welds have pretty poor penetration. So much so that sometimes some customers specify a minimum value of sulfur in their steels. Isn't that funny? Because you want the sulfur out typically, right? That can give you so many problems. But zero sulfur can be a problem too, right? So when you're welding things, you need to worry about some other things. And people have done in these images is kind of cool. You know that in fluid mechanics, you can make these water tunnels or things like those. In material science, physical models are a lot more difficult to do, but they still exist. So they use the sodium nitrate replica. So they are not really welding, because this is now a polymer and they don't use an arc, they use a laser. But what matters in this case is that this material can have surface, there is a surface active element for this material. So when you don't have the surface active element, what you get to see is that the flows move outward. And this is a glass beaker, right? This is not a real weld penetration. But what this shows you is how the heat would be taken to the side, and you can have a wide weld bead. You would have better wetting, but low penetration. Now, if you have, a surface active element, right? And I don't know what the proper name of this weird component is, but with the surface active element, you can reverse the direction of the Marangoni flows and create a jet that goes down, right? And this takes everything that is hot on the surface of the weld pool and brings it into the penetration. This is the mechanism of penetration when you have recirculating flows. Extremely important. Surface active systems, oxygen and sulfur in iron, selenium too, although I never heard of anybody having selenium problems, but I know it, so I'm putting it here. Copper has similar effect with oxygen and sulfur, and also selenium and tellurium. It's not listed here to have a similar behavior, but I'm not sure. And silver with oxygen. Very importantly, you don't see this in aluminum, right? Because you need a specific thermodynamic for having this surface active system work in welding. And in aluminum, the oxygen doesn't survive without reacting. All right, so look at this. These are cross sections of two welds done under the same conditions. And these are in the book of Sindoku on welding metallurgy, which you can access for free through Novel at U of A. And I suggest you do. Amazing book. So here he has these two cross sections done under the same conditions. Look at this, low sulfur steel. This kind of broad bead, these are bead on plate autogenous, right? This broad weld with low penetration. And then the same thing with high sulfur steel. For those that incredible fortune of life, we have plates with low and high sulfur in our lab, which we treasure as if they were made out of gold, because we can do these type of experiments when we want to design, whenever we want to do the science. Keyhole mode, and I have 5 minutes. Keyhole mode we had already discussed is due to the evaporation, but I want to discuss this other mechanism of gouging region. So this is a longitudinal section of a weld that I made. And this is the TIG torch, more or less to scale to how the weld was made. And here we have the cross section of the weld, and here we see the weld from the top. What do we see? This is exactly the same weld. This is the photo before I cut it. What do we see? We see that we have kind of a trailing region kind of where the molten bead is. In this case, I was welding and I stopped the current before I stopped moving. And it froze like this. For most welding experiments, you always want to turn off the power before you turn off the travel speed. We see that has kind of a rim, and then it has this gouging region that looks pretty much dry. And this gouging region, right, and here we have a schematic. We have, in reality, it's not dry, but it's a very thin layer of molten metal. And here you have like I sectioned this and looked at it in detail. And here you see it's more or less tens of microns in thickness, And these formulas you have here, which you don't need to memorize and we will not be using, but they have a special place in my heart because this is my PhD, right? And I could make this prediction and predicted that this is about 50 microns. It's not exact, but I could predict that. And this little rim here is related to Marangoni flows at the edge. I'm not going to worry much about that, but relates to undercutting, for example, which is an important phenomenon. And what we see here is that we have this, the heat of the arc will be digging pretty much directly into the metal, going for penetration, and the pressure of the arc is pushing back this other part, the trailing region. So very different than the mechanism of in recirculating flows. We have the heat on the surface, and then all this is the molten pool, and we have recirculating flows. But in gouging region, the heat of the arc goes straight into the bottom. This part is all hollow. And in this gouging penetration can be so deep that in some cases, and there, for example, the US Navy in the 80s or 90s, they were doing welds in which the torch started to go below the original surface of the plate, right? Because the gouging region was so deep that they could bury the torch without actually touching the plate. Question to you. In this penetration mechanism, and this might be one of the last things we discuss, I would like to hear a word. Do you think sulfur, do you think surface active elements play a role? Do you think high sulfur and low sulfur would give us different penetrations? I'd like to hear. Well, aha. Well, thank you. Somebody ventured the guess. The answer is no. In this case, sulfur plays no role because we have no recirculating flows to increase the penetration. And these are my own experiments. So these I kind of trust. I did the same welds with 6 ppm of sulfur, 230 ppm of sulfur. And we see that for many, for all these welding currents that were giving me this gouging region penetration, sulfur played little to no role. In this case, actually, it's even backwards. I think it's just an experimental artifact. Very interesting. So, for example, in TIG, surface active elements play a role. And that was the case of rocky flats. Subarc welding, they have a gouging region penetration mechanism, and I do not expect sulfur to play a role in those, right? Very, very interesting. So we're gonna stop here, and next week is reading week, and on Tuesday we have the quiz number 4, and I'm going to be listing all the material that goes in. But quiz number 4 will include up to this slide here. Thank you very much, and I'll see you then on Tuesday of the week after next.